have talked about a propositional function, and then some rules of inference so far. Okay, so we have actually trying to use rule of inference to prove that if you are given certain premises, then we can arrive at some conclusion, right? We have used some kind of steps and reasons last time, so that you start with some premises, and then in the end, you have a step-by-step reasoning so that you can get a conclusion. Now today, we are going to do something that is more advanced. We are going to apply, okay, so even, okay, this kind of rule of inference in a high-level way so that we can get a proof for a mathematical argument. Okay, so you will see, okay, you will see there is some similarity between getting a proof or getting some step-by-step reasoning. But you can also see that there are also some difference between these two. One is low level that we have studied so far. You can easily use a computer to check. So if you are given some premises and then you are given some target conclusion, you can ask your computer to check because the rules are already there. But on the other hand, when we are going to look for a proof for a mathematical argument, we need some creativity. Okay, although the logic behind are still the same, we are still using something like modus ponens, modus tollens, whatever. Okay, modus ponens, modus tollens. Okay. So here let me define some terms that you will usually see in a proof. Okay, so some concept. The first one is called axiom. And then the other one is called lemma. And then the other one is corollary. And then the other one is called theorem. And then the last one is called conjecture. So these are some English terms that we should at least learn what they mean. Okay, so axiom. So mathematical arguments is something that mathematicians says they are correct. Okay, so for instance, if x is an integer, then x squared will be greater than or equal to 0. Okay, is that okay? So for any integer x, the square of x is greater than or equal to 0. So this should also always be true. Okay, this is some conclusion that mathematicians find that, okay, they are always true. On the other hand, if I just slightly change it to if x is an integer, then x squared is always less than 0, then clearly this is something that does not fit our expectation, and this is something wrong. Okay, so everything that is correct is something we usually call a theorem. But some of the theorem, you cannot prove it. Okay, so some of the theorem, we need to assume that they are always true. So in that case, so those are like the premises that we always believe that they are true, and they are called axiom. So for instance, something that we need to assume even in talking about integers. So for instance, 0 is an integer, then this is actually an axiom. Okay, you cannot prove that 0 is an integer. There's no way to prove 0 is an integer. But you have to believe, okay? Or assume you believe, then you can talk about what is going on next. Okay, and then for every integer, there is another integer such that it is the successor of it. So 0 has a successor of 1, 1 has a successor of 2, and so on and so forth. Okay, so this does not make sense if you need to prove it. This, we need to believe it. Is that okay? Or even there are some higher level concepts like if you have a group, of some non-negative integers. So you have a group like 0, 5, 7, 11, something like this, a group. Then inside this group of positive or 0, inside this group of non-negative integers, you can always find the smallest integer. Well, this you cannot prove, okay? You believe it, okay? So something like this. So these are about integers. There are also some axioms that we have to believe about real numbers. There are also some axioms that we have to believe about geometry. Okay, so some geometry is like if you have two right angle, then you add up, then you will have a parallel line, have a straight line. The two right angles make a straight line, or okay. So there is some kind of geometry. The classical geometry we will have is if you have two lines that are parallel, they never meet. Okay, okay. So these are some axioms. Under the axiom that we have, so something that we believe. So these forms the premises that we can start at the beginning, and then we can derive new observations. Like, so using the axiom of geometry, maybe we can derive the conclusion that for any triangle, the angles inside adds up to 180 degrees, adds up to a straight line. And then if you have this one, let's say every triangle, the sum of the angles inside is 180 degrees, then every square or every rectangle or every four-sided quadrilateral, then the sum of the angles will be equal to 2 times the 180 degrees. Is that okay? So you start with some foundation, very basic axiom, and then based on it, you can derive new things. Okay? And then just a minor note here. So it is not necessary that parallel lines do not meet. Some mathematicians think parallel lines do not meet. So in that case, you have a group of geometry that corresponds to this axiom. But there are another kind of mathematicians. They believe that, under their assumption, parallel lines actually meet. They meet each other. Then in that case, there is another branch of geometry that corresponds to that. No one knows which one is correct. But anyway, you can have theorems corresponding to this group of axioms. You can have other theorems correspond to another group of axioms. By the different choice of axioms, you will have different theorems. This is the point. Is that okay? Okay. Now, based on axiom, we can prove some results. So usually, those results will be called a theorem. So theorem are something that is derived as a conclusion from the axioms. But then, usually, when we derive theorem, a conclusion, we can have some intermediate conclusion. Okay? So usually the intermediate conclusion that are also theorems by themselves, so you can call it mini theorems, so not that big one. But then there is an English term called lemma that corresponds to that. So theorem is big. That is, people should remember. Lemma are small, and then they are important. Okay, it's like a Lego. So you want to use Lego to build a police station, a big one. But each little piece, you can think of this as a lemma. Okay? Now, once you have a lemma or a theorem, if you do not need to do much thing, and then suddenly you can easily get another one, another theorem, then in that case, we usually call it the corollary. Corollary is some easy theorem from a theorem. Okay, very easy. So for instance, let me see. Yeah, we will see. Okay. And finally, there is this word, conjecture. Conjecture is really something that is not proven. So nobody knows whether they are correct. Conjecture is something that is likely to be true. But still, nobody knows whether it is true or false. Okay. So in that case, okay, you can always say something like, I will be rich. Or, okay, I will have a lot of food tonight. Okay, so this can be a conjecture or a guess. But mathematicians do not make conjecture like this. Okay, they try to make some conjecture that is influential or that has some good effect afterwards. So in computer science, okay, so computer science we have a theoretical computer science. We will classify problems that we can solve usually into different groups. And then two of the groups are, one of them is called P. So there are many problems in this group. Let me call it P. And then there are many problems in this group called MP. Okay. So P are problems like you can have an efficient algorithm to solve it. Okay, so if you have a what is meant by efficient? Oh, efficient algorithm solve it like you have a bunch of numbers, you want to arrange it from small to large. Or can you do so? So what is meant by efficiency? You can have a procedure, step-by-step procedure to do that, then it is okay. So for this kind of sorting problem, we can pick the smallest number and then pick the next smallest number and so on and so forth. So you can do that, right? It's quite fast. So in that case, there is a group of problem called P, okay? There is also another group of problem that you can check. You just check whether the solution is correct. But even though you don't know how to solve it. Okay, so for instance, a problem like you have a lot of row junctions. So these are okay. Let's say this is so some rows. So there are row junctions here, and then you want to place some policemen at the row junctions. For instance, I may place a policeman in this part. I may place a policeman in this part. I may place a policeman in this part, let's say something like this. And then I may place a policeman in this part. And then I may place a policeman in this part. Okay, let's say I'm placing 5 policemen. Okay, I'm placing 5 policemen here so that for each of the road, not enough. Okay, so yeah, let's say. So for each of the road, this road, this road, this road. No, there are many. Okay, let's place more. So the target here is that each policeman here can monitor a road that it can look after. Is that okay? So we want to ask, is 7 policemen enough for this map? If 7 is enough, maybe we can ask, is 6 is enough, and so on and so forth. Is that okay? Do you understand the problem? So for this problem, so if there is a solution, let's say 6 policemen is enough, then we can check a correct solution very quickly. You just tell me where are the policemen that you should place, and then where are the policemen that you should place, and then I can check one by one whether each road is being monitored by at least 1 policeman. Is that okay? Now, so there are many types of problems like this. So this requires just, you give me a solution, a correct solution, and then I can check quickly whether your solution is correct. Okay, so this type of problem, we call it NP. So somehow, it's not meaning not P, but it is like just not as strong as P. Okay, so P, you need to find a way really to tell me how I should place these 6 policemen. But on the other hand, if a problem is in this part, you just need what? You just need to check a correct solution is correct. Okay? So you understand the difference, right? So there are 2 groups of problems. One is in P, one is in NP. And there are actually many other groups. Some problems you do not have any efficient algorithm. So there are other problems outside. Now, so for many years, okay, people now understand what types of problems are hardest here. What is the most difficult problem here? And for any of these difficult problems, nobody has found any way to solve it, to calculate let's say this problem, to calculate where to place the policeman quickly. So for many years, people believe that, it's just belief that there's something here, which is super hard, that cannot be in here, in this group. You cannot compute it. You can just check it, I can do that. But compute it is super difficult. So people will think that these 2 things are not the same. Okay. But then, this is a conjecture only. Nobody knows. So far, it is still one of the open problem in computer science. And this problem was, a long time ago, it was $1 million US. So if you can solve it, okay, then you can have $1 million US. But so far, nobody knows. Okay. In computer science, there are other questions like this. So when you study algorithm or theory of computation later in your course, you will know more about this. Okay. So it is the P not equal to NP problem. Okay. Or P. So usually it's like this. We don't know. So this is the status. Nobody knows whether they are the same or whether they are not. Okay, so we have actually a lot of conjectures. So conjecture. So these are something that is significantly important. Okay, because we use cryptography. We use cryptography to help us to make our message secure. So if I want to send something secretly to Coco, let's say, I may try to make my message spoken in some very strange way so that anybody in between cannot understand what I'm talking about. Only Coco and I knows what is going on. Okay, but how can we make this happen? Okay, so currently we rely certain conjecture that the way to break our agreement is hard. There is no efficient algorithm, no efficient method to solve it. It is at least some problem that is very, very hard to solve. Okay, but on the other hand, if one day P turns out to be equal to NP, so even the hardest problem here can be solved quickly, then some of the cryptography scheme will fail. Okay, because in that case you can break down the code. Okay, so these are something that is we can use it. So if they are not equal, we can use it actually. This is a good thing for us. If they are not equal, we can use it. If they are equal, that is also good because there is no more hard problems inside this part. Okay, so these are some keywords I want to introduce to you. Okay, now the method of proving. So we are going to look at different ways of proving something. So the first one that we want to talk about is direct proof. So we try to prove something directly. And if there are direct proof, of course, there are going to be what? If there is direct proof, then there is indirect proof. Very good. Okay. So we have also indirect proof. And indirect proof, we are going to introduce at least two types. So one is we prove it by contraposition. And then the other is we prove it by contradiction. Okay, so these are something similar. Okay, so let's take a look at some example. Okay,